My name is Szymon Romik. I'm a software engineer from Intel. I am developing PMDK libraries, and I am responsible for Pmemkv library and C++ bindings for Pmobj library. One announcement at the beginning. I was attending a previous session and I was sitting right there behind all of you, and I noticed that the screen is quite small, so I can see 3 slots in front of the room, so you can change your seat, because I am using small fonts on some slides, just for your convenience. Okay, let me start. This session title is Persistent Memory Programming Made Easy with Pmemkv. And it turns out that it is possible to make it very easy. And I can talk about Pmemkv API about 10 minutes, and you will probably know everything you want to know. But for better understanding, I have to describe why there was a reason to make it easy, because it turns out that it is sometimes difficult to do persistent memory programming. And I will start with this. I will describe why persistent memory programming is difficult. And then I will go to Pmemkv design. I will make overview of engines available, language bindings available, and only after that I will show you an example of Pmemkv application. So it will be shown, but you have to wait for it. At the end I will briefly talk about latency, sources of latencies, and the performance of Pmemkv. And we will have time for questions and answers. So, just in case, if we won't have more time for question and answers section, just don't bother and ask me questions during my presentation. Okay, so let me start. Why Pmemkv? So, just to make sure that we are on the same page, and for those of you who wasn't able to attend Andy's presentation about PMDK essentials, I will briefly talk about persistent memory usage modes. We have 3 main usage modes. First one is memory mode, where we are using persistent memory in volatile mode, just for its capacity. Then we have storage over updirect mode, where we are using well-known file I/O API. This is for, you can use it when you don't want to modify your application. And we have updirect mode, the most interesting one, because you can gain the most using this mode. And Pmemkv is designed to take advantage of updirect mode and persistent memory. So persistent memory is exposed to the application by files with PM our file system. There is in place persistent, so there is no paging, no context switching, no interrupts. You have this straight line over here means that you have direct access from your application to persistent memory to take advantage of its byte addressability. And SNIA programming model describes the usage of the persistent memory in updirect mode, and you can use it just like here on this example. Nothing new here. You are opening file, you are mapping it, you are getting a pointer, and from now on you can start manipulating this pointer and start using msync. So it looks very easy, but it is not. And this is one of the reasons why. One can think that if you copy data to the memory mapped area by calling memcopy or memset, the data is here, but this is not true. It must be true, because the data may stack on CPU cache. and to make sure that data is persistent, we have to flash it. This is the msync call in previous slide was for, but this is not optimized way for flashing your data, because data flashed by msync are aligned for page cache. So we have to use one of the available instructions and call it from user space. You have see the list of available, of possible instructions over here. And once we have it, we are sure that the data is persistent. So here is a simple example where we are using Pmempersist instead of calling msync. And Pmempersist is a function from libpmem library. This is another library from PMDK library set. So this is more optimal than using msync, but this is still not transactional. Imagine a situation, consider a situation where we have a crash during execution of this line. So we are trying to copy simple string hello world to persistent memory. The crash happens, and what is the result? Option 1, 2, 3, 4, or 5. Everything is possible. Because Pmempersist is still not transactional. So because of this, you have to implement your own power fail-safe algorithms, or you can use another library from PMDK library set called Pmemkv, which provides transactional API. So instead of application responsibility called flashing, we have another consistency. And this is a very simple example of Pmemkv with C++ bindings usage. I don't want to talk about this during this session, but tomorrow we have another session creating C++ application with Pmemkv. I will be presenting it together with Sean. So I highly encourage you to join me tomorrow afternoon as well. Okay. So it is not easy. I would say it is relatively difficult to persistent memory programming. And the question is now how to make it easier. So we have a statement, API flexibility increases complexity. I think everyone will agree with that statement. But also API flexibility is not always desired. Another statement, usually the bigger barrier to adoption, the better performance gains. And again, it don't have to be true for some specific workloads. So we must do some trade-off to make it easier. We have to reduce our possible workloads, reduce API, and still target a lot of possible customers. So the answer is local key value data store. The API provided by key value data store is very straightforward, well known. This is making this statement not true. And the reason why we want simple API is that we want to create different language bindings for the library. And in current cloud-native computing, especially in current cloud-native computing environment, where there are many high-level languages are being used. So we already agree that we want to create a key-value data store because of the API simplicity and because it matches a lot, very many workloads. And another reason why we are creating a key-value data store is that it can take advantage from persistent memory characteristics. This above, persistent and big capacity sounds quite obvious for key-value data store. We want to have as many key-value pairs as possible and make them persistent. But we can also utilize persistent memory by addressability. And this diagram shows exactly why. On the left side, we have normal key-value data store where data resides in some kind of storage. And in order to read the value, we must copy it into buffers residing in DRAM. So what does it mean? If we want to access, if we want to read a single byte or single cache line sized value, we have to copy the full page cache into kernel and read only after that copy the data to DRAM. And if we have local persistent memory key-value data store, we can have direct access. So we can very easily take advantage of persistent memory byte addressability. So that was basically the reason why we created this library, to complete PMDK library dataset and to take the fact of this, take advantage of the facts I just listed. Let's move on into Pmemkv design. We have a couple of goals for Pmemkv. I split them into technical and community. So let me first discuss the technical goals. So first of all, we wanted to create local key-value data store without networking related latency. We wanted to provide very simple API to the user with idiomatic language bindings. And another goal was to make design in this way that we can very easily add new storage engines. So all engines are very pluggable in our library architecture. We wanted to optimize API for the library to take advantage of direct access. I will show you how it works in an example later on. And to limit copying to or from DRAM. Because we want to have pluggable engines, we decided to make very flexible configuration, not limited to single storage algorithm. And we provided generic tests in the library for different kinds of engines. I will talk about the different kinds of engines on a separate slide. And the community goals. So Pmemkv is a part of PMDK library. Because of that, not only because of that, it is open source with friendly licensing. As it was mentioned on the previous sessions many times, you can just start using it without telling us, or you can just cut off some code and implement it in your application. We are here in the GitHub pages. Outside contributions are welcome. And in fact, we already have some external contributions. We have some clients already. But what is more important, we can provide you stewardship. We can help you to understand how to make persistent memory programming by implementing engines with Pmemkv. So you can treat engines like a good example of the Pmemkv usage. We can validate your engines on your hardware, and of course make code reviews. We are not merging everything you write. And we have standard comparable benchmarks available. I will talk about performance and sources of latencies later. And this is a big picture of Pmemkv architecture design. In the very middle, you can see the red boxes. This is Pmemkv core. And I want to accentuate that Pmemkv core is almost not aware of persistent memory. I mean, it does have API optimized for persistent memory, but this is only C++. Pmkv core could be written by everyone, even by a programmer who who didn't program persistent memory before. But on the bottom, we have engines and dependent libraries. And as you can see, some engines are implemented in our repository. In order to implement persistent memory engine, you must have a knowledge about persistent memory programming. And some of them are ported from another projects. For example, all of our current available engines which are persistent are written in libpmopt. Some of them are volatile and they need to be linked with Pmemkv, and some of them are concurrent and must be linked with TBB. On the top of this diagram, from the other hand, we have applications, and we have some native interfaces to start working with different languages. Okay, now I will move to configuration details. As I mentioned before, we wanted to make it very easy to add any engines you would like to have. So we decided to make it a config structure, which is basically an ordered map. It collects key value pairs, parameter name, and the value of the parameter. We can store limited types over here. It is integers, unsigned integers, doubles, strings, and arbitrary data, which means it takes pointer and the size of the buffer. One of the reasons why this is limited is that we want to make it very easy to translate it to higher level languages. The config structure resides on stack, and it means that if you want to pass an object which allocates memory in DRAM, you have to pass also the destructor to avoid memory leaks. And this is important part of design, the life cycle. So what is residing in DRAM, what is residing in persistent memory? I will show you in this example. So first we are making configuration, we are preparing our config structure. It of course resides on DRAM. In this case, we are passing a path to a file. So it means that the engines we want to set up will be in persistent memory and the size of the file. Then we are creating DB object, which is a volatile object for managing our engine which will reside in persistent memory. And finally, we are calling an open function on our object KV. You can see that we are passing two parameters. The second one is a for prepared config structure, and the first one is a string with the name of the engine. It is very simple. API is very simple, but this function call do a lot. It allocates in persistent memory. It creates a file in persistent memory if it wasn't existed before, and it creates an engine, data structures in persistent memory. So from now on, we have a connection from our volatile manager and an engine. After that, we can do our work here, which will be most often putting some new keys and values and getting the values, the values from given key. And then we can close our database by close function. You can notice that the connection disappeared, and we can delete our volatile Kv object. The ownership of configuration structure was passed to the Kv object with this open call. So config structure was also destructed, and all dependent parameters we passed. But you can see that our engine and keys and values remains in persistent memory. And when we will be opening the database again, we'll first check for consistency, and then initialize connection again, and we can start using our engine again, even after crash, power failure, or another reboot of application. And let's move to the engines. So this is the list of all available engines right now in Pmemkv. Engines contributions, of course, are welcome. We have a couple of types of engines. First of all, we recognize ordered and unordered engines. So most probably some kind of hash tables and trees. We recognize persistent and volatile engines. Again, we can use persistent memory for its capacity, not persistence. So this is the reason behind volatile engines. And we can recognize concurrent and single-threaded engines. All of them have different generic tests. Now I will talk a little bit about this test. So we are testing engines, depending of course the types they are, with some simple functional tests, and with some tools, with Memcheck, Hellgreen, DRD, with these three you are most probably familiar with. But we have two other tools, Pmcheck and Pmreorder. Pmcheck is an extension to Valgrind, developed by PMDK team, and it helps you find bugs in your libpmemopt based algorithms. So very important tool if you want to test your persistent engines with in Pmemkv. And Pmreorder is another tool developed by PMDK team. It basically checks if your persistent algorithms are consistent. And the way it is doing this, it is shuffling the order of your stores and compares the results. You can read more about these two tools in our web pages. So coming back to engines, some of them are experimental, some of them are fully validated. The main engine and recommended by us is concurrent hashmap. The engine name is in Pmemkv is CMAP. Actually, it is not implemented in Pmemkv, it is implemented in libpmemopt C++ bindings repository by our colleague Sergey. So if you are, if you want to hear more details about implementation, because this is quite sophisticated and complicated piece of code. We have concurrent hashmap and we have persistence. So you can imagine the complexity. But it is great. It scales and it keeps flat the persistent latency. Yes, this is. So I hope I already recommended this engine. We have volatile engines, which are not experimental, and we have some experimental engines based on well-known concepts. And this row has red background because this engine is under development. It is sorted concurrent map. As I said, implementation is ongoing. It will be also available from libpmemopt C++ library and implemented and exported as an engine to Pmemkv, and it will be designed with skip lists. Okay, so as I mentioned before, we have some clients already, and this is great because we can gather more and more requirements from them. And one of the requirements from the client was to make multiple engines within the single memory pool. Because before that, we thought that it would be good enough to correlate an engine, single key value data store with a single memory pool. So this is one of the reasons why we decided to make the configuration of our database very flexible in order to make custom configuration of your engine. And right now we are working in some more generic solution for multiple engines within the same memory pool. So it will be obligatory parameter for Pmemkv-based engines. And again, if you want to hear more about these concepts, root object, persistent pointer, I redirect you to another session tomorrow about creating C++ applications with Pmemkv. This is the prototype API, but I'm not going to talk about this right now. And finally, we move to language bindings. So, simple API makes easy implementation of high-level language bindings with small performance overhead. This is quite important because we make some comparison benchmarks between different language bindings and native C and C++ API, and it turns out that high-level language bindings have around 5%, 8% overhead with latency. Right now we have 4 available language bindings. You can find them there for Java, Node.js, Ruby, and Python. However, their API is not functionally equal to the native C and C++ counterpart. And the reason why is that we made recently quite significant API changes, and we are still looking for more feedback from our customers. Pmemkv is now released in version 0.8. It means that it doesn't mean that the library is unfinished. As I said, we want to gather more requirements for our potential customers. So one of the difference between functionality of language bindings and native C++ API is that we are configuring the engine by JSON string, and because of that, multiple engines within single memory pool is not possible. But we have a plans and we have a roadmap where we are planning to remove those gaps. And finally, I can show you the full example of Pmemkv usage. I could start this presentation from this slide and finish 3 slides later, because this is all what you need if you want to start programming with Pmemkv. So we have well understood key value API. There is nothing new to learn. It is inspired by key value data stores like RocksDB and LevelDB. We have API for managing lifecycle, as I already shown on previous slides. We have open and close API. We have operations API, put key value, get key value, or you can use a callback. I will describe the difference on the next slide. We can remove the key. We can check if the key exists. We have error message static function, which basically returns a string with readable error message. And we have iteration API. We can count all elements, we can get all elements, and we have range version of above for ordered engines, of course. Because for unordered engines, it is not possible to call below, above, and between. We are not comparing keys. And this is quite important. Pmemkv is not limited to the API above. Right now, this is the all existing API, but in future, some specific engines might provide some extensions and like batch update. We already have one request from the client about this extension. So this is full C++ example. I mean, not full. I skipped the setup of configuration because with this font it did not fit into the screen size. So first of all, we are opening our database. We are putting key and value. So in this example, we are getting John, and we are checking if John still exists. And this is important. And we have get. We are copying the value for John, which is his phone number, to previously allocated on DRAM string variable over here. And over here, we are getting John's directly from persistent memory. And this is by passing a callback to the getAll function. And the reason why we are doing it by callback, because we have to lock other from reading the value when the user have direct pointer to persistent memory. And after that, there is nothing surprising. We are checking with exist if John still exists. Yes, he's existing because we are removing him later. And we can close our database. So, very straightforward API. And this is Node.js example. The same situation, but even less coding. Creating database with JSON string, putting key and value, getting value from given key. Here is copying the data, and over here we have direct access to persistent memory. We are removing key, checking if it exists, and stopping engines. And the similar simplicity we have for other high-level language bindings. So I am not going to show it. I'm not going to show it to you. And now, a couple of words about latencies and performance. So as I already mentioned, we have small latency overhead for high-level language bindings. I said that this is between 5 and 10%, depending on language bindings, depending on workload. And one of the source of language bindings latency is the number of round trips between high-level language and native code. We have to translate bytes to UTF-8. We are creating high-level objects like string, byte arrays, reference type, callbacks, or closure lambdas, and so on. So it all makes the 5–10% latency overhead comparing to the C++ counterpart. We have Pmemkv core related latencies. And again, depending on the engine, it can be either searching indexes in DRAM, or if we have persistent engines, the overhead might be related to managing transactions or allocating persistent memory. And finally, we have persistent memory latency. What is worth to mention is that reading data from persistent memory is much faster than writing. And another source of latency and difference in performance is that performance varies based on traffic pattern. We have something called ECC block in persistent memory, and it means that the fastest possible bandwidth we can get is for workloads equal to 256 bytes. And again, read versus write latency. This is last slide. This is the last slide I have. It tells a little bit about performance of our CMAP engine. Again, it is implemented in Pmemkv C++ library as one of the persistent containers. If you need to know more about, if you want to know more about this engine, please ask Sergey. And in Pmemkv we have a separate side project, side repository called Pmemkv tools. It is in separate repository for a very simple reason. We are using over here benchmark inspired by dbbench, and we can't make it under Pmemkv license. So you can get over here. The interface and the usage is again quite straightforward, and you can play around with benchmarks depending on your workloads, depending on the engine you have picked, and your hardware, of course. So this is how by using this tool, I have tested the CMAP engines, and I make a benchmark for 16 threads, and I used read while writing. Read while writing benchmark works like this: that there is one thread which is writing, and all other threads are reading. So this is quite good benchmark because it might represent your workload. I tested it for the keys key size of 16 bytes and value size for 200 bytes in order to make it fit into one ECC block. And for 16 threads, I added 20 millions of pairs, key value pairs. I had a throughput 1,400 megabytes per second with flat P99 latencies, and average latency equal to 2.3 microseconds. So I think these numbers are quite impressive. You can check it by yourself. You can just run benchmark available in this repository. And before we move into question and answer section, I want to invite you to the tomorrow session by Vitune guys. They will be describing how we can optimize PMDK-based structures with Vitune. And in fact, we used this feature for optimizing our engines. So it might be very interesting for you. And yes, that's all from me. Now, if you have any questions.
So, does anyone have questions for this?
就是我们也测过这个 Pmemkv 的性能，但是我们测出来感觉你可能写就几十万，读差不多最高那个 CMAP 300-400万左右，我感觉完全没有怼满 AEP 的那个极限性能。对，我觉得这个因为我们怼满，我们当时用4片 AEP 测，它的极限性能应该能在24GB 左右，换算出来 KV 对应该是肯定是能上千万的，但是我们测那 Pmemkv 就确实是只有几百万，然后写的话可能就更差一点。这个是因为 Pmemkv 造成的吗？还是我问你。
So I will do the translation. So he is asking that he tested Pmemkv and he cannot get the performance for the full speed for AEP, and he used like 4 AEP together, and the performance is not as good as expected.
And what size of keys and values did you use?
1K.
1K. 1K by.
Okay, so it shouldn't happen. We can discuss the details of your setup configuration offline, because I didn't want to put the numbers on this slide because of some issues related to Intel's policy. But as I said, this benchmark tool is very transparent. We have engine available for everyone, and for specific workloads, I just mentioned for keys size equal to 16 and for values equal to 200, I make it much faster.
And he is also asking whether it is due to the constraints from Pmemkv.
What the question is for AP theme, the maximum speed is roughly 24 gigs, right? You can see roughly 6 gig by 4 per theme, right? So the maximum speed for 4 gig for theme is roughly 24 gigs, right? But what he had measured is roughly about maybe for 24 gig, maybe it should be more than 10K 10K transaction, but right now it's only roughly 10%.
I want to make.
It's there.
I want to understand it correctly. So you were measuring performance of LibPMOpt or LibPMOpt based engine, and comparing the bandwidth results.
I test the CMAP and tree. So CMAP and the tree use Pmem object, but its write performance is not as good as AEP performance. 我就是说我用了那个 tree 3跟那个 CMAP， 然后它
Yes, I understand.
它的写就是它写性能，无论是读还是写都没达到，都不像 AEP。
这个可能跟你那个 workload 有关，所以后面可以跟我们团队再具体去看一下这个 workload 的情况，包括配置、硬件和软件。
就是说，那下一个问题就是说，最理想情况下 Pmemkv 能不能达到AEP 的最高的情况
Okay. So he is also asking for the best practice. Can Pmemkv reach the highest speed of AEP?
Okay. So first of all, different engines have different sources of overhead. If you have ordered map, there is additional latency for ordering the key value pairs into your tree or any structure you are using, right? And for unordered map, unordered engines, you have also overhead of calculating or rehashing, reallocating, and so on. So you can't get the maximum possible bandwidth when you are using this kind of library. I mean, it won't be as fast as you will be just copying data, right? And if you want to get the maximum performance, your writes for a single method for a single put must not be bigger or must be almost the size of ECC block. This is why in my benchmark I used the value size equal to 16 bytes and the key size equal to 16 bytes and value size equal to 200 bytes. And that's all I can say. Also, managing transactions, person memory allocations are also the source of additional overhead.
Let me add one comment. If you want a key value store that is transactional, then we have to write about 2 bytes for every 1 byte you write. Of course, you won't see the bandwidth of AEP because we're writing metadata and an undo log and everything. If you want a key value store that's non-transactional, of course, then we can make it faster. So transactions are not free, but they're important for,
what cost of transaction? Half of the performance or more?
to make a transaction so that you can recover a crash, right? So on a crash, you need enough data to recover to make the key value still consistent. So that means on every time you write something, you have to write the old. Yeah.
I want to ask the transaction may degree the performance percentage.
Yeah, so the question is, you guys can't hear it, what's the percentage of performance degradation due to transactions? And of course, it depends on what's being modified. So if, like I said, the 2 to 1 is for the metadata, like the data that we're changing during a transaction. But if you're storing a new value that's 1 megabyte, we don't copy that twice, because that's a new data. So changes to old data have to be copied twice, because we have to be able to undo the change. Changes to new data are just copied once. So it's very dependent on the data pattern.
So the transaction maybe degrade half of the performance because you write 1 byte maybe undo log and.
I would say the transaction degrades the performance by half if you're modifying an existing value. If you're adding a new value, it's less than that. And it depends on the size, right? And it's different for different engines, as Shimon was saying. So it depends on the engines. So you look at your needs, right? If you really need transactional updates, there's a cost, right?
That's still going to be far faster than having to create a connection over a network to a key value server, even if that server is using persistent memory. If you have to go across the network and persist that on a key value server, then you're going to be an order of magnitude slower already. So you are doing this in memory, in your server, and persisting it in your server with no network traffic, which will be far faster.
And faster than storage too for that.
On your Redis server, it is also doing a transaction. You just don't see that. But that's the performance you get. That's the performance we've always had from Redis. This is all in memory, and it will be, order of magnitude faster than doing it otherwise.
It's a good question.
还有没有别的问题？如果没有的话，我们就进入下一个赛。Thank you.